This is Algebra 2, Unit 9, Lesson 1 on imaginary numbers. Now, when we were talking about real numbers in the real number system, it is not possible to take the square root of a negative quantity, because whenever a real number is squared, it is non-negative. So this fact has a ramification for finding x-intercepts of a parabola, as exercise 1 will illustrate. Alright, so on the axis below, the sketch of y equals x squared is shown. Now consider the parabola whose equation is given the function notation at f of x equals x squared plus 1. So how does this graph shift? Well, since it's x squared plus 1, that means it's going to shift up 1. Because of the plus 1 here, it's affecting the intercept. So x squared plus 1, if I sketch this, the 0, 0 is going to go up to here to be 0, 1. And your parabola is going to look the same, it's just going to be shifted up 1. Alright, so it should look something like that. Not perfect. Okay, now what can be said about the x-intercepts of the function y equals f of x? Well, x-intercept is where it crosses the x-axis, correct? Yeah. So this says the x-intercepts don't exist. They don't exist. So, or because the parabola does not cross the x-axis. Okay, now if we look algebraically, show that these intercepts do not exist in the real number system by solving the incomplete quadratic x squared plus 1 equals 0. Alright, so if we take x squared plus 1 equals 0 and solve it, move the 1 over, x squared equals negative 1, and then take the square root of both sides, we get x is equal to plus or minus the square root of negative 1. Is that possible? No, that is not possible. That's not a real number. Alright, so since we cannot solve this equation using real numbered, we introduced a new number called I, which is the basis of imaginary numbers. Remember back in Algebra 1 I said there was stuff that you couldn't factor because it's imaginary? Well, this is what we're talking about when I told you it was coming in Algebra 2. Alright, so now we can actually find the square root of a negative number, but it is not a real number. The value I is equal to the square root of negative 1. So when you simplify a square root, you have to take into account if negative 1 can be taken out of it. When you take the square root of a negative, you can rewrite this as the square root of 9 times the square root of negative 1. So I is equal to the square root of negative 1. So the square root of 9 is 3. The square root of negative 1 is I. So it's going to be 3i. The square root of negative 100, it's 100 times negative 1. The square root of 100 is 10. The square root of negative 1 is I. So it's 10i. Alright, the square root of negative 32. Well, 32 is 16 times 2, and then times negative 1. That'll give you negative 32. The square root of 16 is 4. The square root of negative 1 is I, times the square root of 2. 4i times the square root of 2. You can also write this 4 times the square root of 2i out here, but sometimes it looks like the I is under the square root, so I usually put it in front. So putting it in front is fine. So 4i square root of 2 is fine. Alright, the square root of negative 18. Well, what perfect square goes in 18 would be 9. So that would be 9 times 2 times negative 1. The square root of 9 is 3. The square root of negative 1 is I times the square root of 2. 3i times the square root of 2. So these are imaginary numbers using I because we have to take the square root of negative 1. That's how it works out. Alright, now let's use that fact to solve these incomplete quadratics. Place your answers in simplest radical form. Alright, now when you have 5x squared plus 8 equals negative 12, the goal is to get the x by itself. So the first thing we have to do is subtract the 8. So 5x squared is equal to negative 20. Divide by 5, and you get x squared is equal to negative 4. Alright, take the square root of both sides. Remember, when you take the square root of both sides, there's actually two answers. There's plus and minus. the square root of negative 4. Okay, so x is equal to plus or minus, well, negative 4 is actually 4 times negative 1, so this is going to be plus or minus 2i. So x is equal to 2i, or x is equal to negative 2i. All right, 1/2 x squared plus 20 is equal to 2. Get the x squared by itself, subtract the 20. 1/2 x squared is equal to negative 18. To get rid of the fraction, we multiply both sides by 2. We get x squared is equal to negative 36. Take the square root of both sides. Don't forget it's plus or minus. All right, so the square root of x squared is just x. The square root of negative 36, well, we know it's going to be 36 times negative 1. Square root of 36 is 6. The square root of negative 1 is I, so it's plus or minus 6i. Don't forget the plus or minus, because we took the square root. All right, 2x squared minus 10 is equal to negative 36. Add the 10. 2x squared is equal to negative 26. Divide by 2. X squared is equal to negative 13. Take the square root of both sides. Don't forget it's plus or minus. All right, now 13 can only be written as 13 times negative 1. So x is going to equal plus or minus, the square root of negative 1 is just I, times the square root of 13. And that's as far as you can go on that one because of the 13 not having any perfect squares in it. But there we go. All right, so you have to keep in mind when you take the square root of a negative, it becomes a negative 1, it becomes I. All right, so which of the following is equivalent to 5i times 6i? Well, let's see. 5 times 6 is 30. I times I is I squared. All right, now, if we're going to work I squared out, we have to know what I squared is. Well, we know that I is equal to the square root of negative 1. What would I squared be? Well, it would be the square root of negative 1 squared. Well, what's the square root of negative 1 squared? Well, the square cancels out the square root, so that's just going to equal negative 1. So this is going to be 30 times negative 1, which is negative 30. So this is going to be number 3. Okay, this leads us into the powers of I pattern that we're going to talk about next. Powers of I display a remarkable pattern that allow us to simplify large powers of I into one of 4 cases. This pattern is discovered in exercise 4. So basically what we're going to look at is how we can apply the powers of I and figure out what a value is based on 4 cases. All right, so this is all based on that I is equal to the square root of negative 1. So I the first is just going to be I. We know that. Technically it's the square root of negative 1. I squared. Well, we just did that on the previous example. It would be the square root of negative 1 squared. Well, what's the square root of negative 1 squared? Well, doesn't the square cancel out the square root? So I squared is equal to negative 1. All right, now let's apply the powers of exponents. How do we write I cubed using I and I squared? Well, isn't it I squared times I? Yeah. I squared, we just said, was negative 1, times I is equal to negative I. So I cubed is negative I. How could we write I to the 4th? Well, isn't it I to the 4th I squared times I squared? Well, I squared we said was negative 1. And it's also negative 1 again. Negative 1 times negative 1 is positive 1. Oh, there we go. All right, I to the 5th. Well, can't we write that as I to the 4th times I? I to the 4th is 1. I is just I. 1 times I is I. All right, I to the 6th. Well, there's lots of ways we can write I to the 6th. Why don't I write it as I to the 4th times I squared? That gives me I to the 6th. I to the 4th is easy because that's just 1. I squared is negative 1. 1 times negative 1 is negative 1. All right, I to the 7th. Well, that would be I to the 4th times I to the 3rd. I to the 4th is 1. I to the third is negative I. 1 times negative I is negative I. All right, and then I to the 8th would be I to the 4th times I to the 4th. 1 times 1 is 1. All right, so look at our pattern here. Your pattern is I, negative 1, negative I, 1. I, negative 1, negative I, 1. The pattern will repeat every single time. So the trick to doing this is to get the highest power of I to the 4th that you can, and then multiplied by the rest of it. All right, so I'll explain what I mean by that. So using that pattern, what is the biggest 4th power that goes into 38? Well, it would be I to the 36, right? You want a factor that's divisible by 4. So I to the 36, because that'll equal I to the 4th. All right, so I to the 36 times I squared gives you I to the 38. Now, where this is coming from is I to the 4th to the 9th will give you 36. And we know that I to the 4th is 1. So it's 1 to the 9th. And then I squared is negative 1. Oops, times negative 1. So 1 to the 9th times negative 1 is just going to be negative 1. So if you can get a factor divisible by 4, we know it's always going to equal 1. The exponent divisible by 4. Get the biggest one that you can get. All right, so the largest exponent divisible by 4 for I to the 21st would be I to the 20th. I to the 20th times I. All right, so I to the 20th is a multiple of 4. So since that's a multiple of 4, it's going to be divisible by come out to be 1. Times I is equal to I. All right, what is the biggest biggest exponent divisible by 4 that we can break 83 into? Well, it would be I to the 80th times I to the 3rd. That gives me 83. This is divisible by 4, so that means it's going to equal 1. I to the 4th to the 20th is 80, so this is going to equal 1 times I cubed. Oops. And I cubed, remember we said was negative I. It says so right here. 1 times negative I is negative I. All right, and then I to the 40th, well, that's divisible by 4, so that's going to equal 1. Because remember, this is really going to be I to the 4th to the 10th power, which is 1 to the 10th, which is 1. All right, so get the biggest exponent divisible by 4 that you can, and write it as a product with another. All right, so using those powers of I, see if you can figure out the answer to exercise 6 here, and we'll go over this in class the next day.